Chapter 10, Network Segmentation and Virtualization. This week, we're going to break with our mold here a little bit. Chapter 10 is actually a pretty wide-ranging chapter. It covers everything from classful networking, classless networking, classless interdomain routing, virtualization, virtual machines, vSwitches, virtual networking, things like VLANs and that type of thing. And it's definitely an important chapter. And by all means, as you're going through this week's material, do the reading, do the review questions, cover all these other areas. We're going to dedicate our lectures this week, though, to just one part of that. And that's going to be IPv4 and specifically IPv4 subnetting. Why? Why do we care? Honestly, if you take nothing else from this entire course, take this from it, right? We need to understand how to subnet in IPv4. It's not an exaggeration to say that there is not really very many paths forward in a career in IT if you do not understand these concepts. It's that critical. So let's get a reference point here. Where are we? Well, if we go back to our TCP/IP model, IPv4, and that stands for Internet Protocol, and there's two of them. There's Internet Protocol version 4 and Internet Protocol version 6. Our discussion this week is strictly on IPv4, and that lives right here at layer 3 of our TCP/IP model. The internet layer. Makes sense. Internet protocol at the internet layer. This is where logical IP addresses exist. And by logical, I don't mean like a Vulkan logic kind of thing. I mean, they're not physical. Physical addresses are MAC addresses down here on layer 2, right? It's a physical entity. It's actually burned into the chip. IPv4 addresses are not. And they can be assigned, they can be reassigned, they're basically relative. So we're thinking in terms of logical values. So let's take a look at what an IPv4 address even is. Well, you've seen them. I mean, we saw them earlier in this course. We're looking at them right here. And it's made up of two primary parts. We've got the actual IP address right here. And here's one we've probably seen many, many times before, 192.168.1.1 or 1.100. It's like the most commonly used network segment probably on the planet because it's used for home use. This is the actual IP address itself. Now here's the thing. An IP address by itself is completely useless to me. Absolutely useless. It's about as useful as a screen door on a battleship. Seriously. I need the second half, the second part of my IP address, called the subnet mask. The subnet mask puts my IP address into perspective. And you're like, what does that mean? What's going on there? All right, well, look. Let's look at the address itself. Let's see how it's built. The IP address is a 32-bit value that's comprised of 4 dot delimited octets. Dot delimited. Here's our little dots right here, right? So octet, 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 octet. 4 fields, actually. Why octet? Octagon, octopus, 8. Each of these values, each of these fields is an 8-bit number. 4 times 8, 32. That's where we get our 32-bit IP address from. Well, some of these octets tell me what my network identifier is. What network is a host on? Other parts of the number tell me on that network what identifies the host. Now, I'm using the word host here instead of computer, but I mean, traditionally it was a computer, but a host can be anything. It can be a wireless printer, it can be an iPhone connected via Wi-Fi, an iPad, Samsung device, whatever. It makes no difference. IP phone, you name it. The subnet mask is what tells me what part of the address refers to the network and what part refers to the host. In this case, What we're looking at right now is something called classful networking. In classful networking, a subnet mask of 255 means, or a field within the subnet mask that's 255 means network. So for this address right here, 192.168.1.100, and the fields line up, right? 192.168.1 refer to the network. So I'm on the 192.168.1 network. Where there's a 0, and in classful networking, it's either a 0 or 255. Where there's a 0, it refers to the host ID. Right? Let's take another look at this. Well, my classful networks can be broken up in a variety of ways. Right? One thing I forgot to mention, if this is a 32-bit number, how many IPv4 addresses do you think there are in the world? IPv4, 32-bit number. The number is 4 billion and some change IP addresses. Now, when this was created back in the late 1960s, and the precursor to the internet, the ARPANET, had all of like 4 hosts on it, 4 billion addresses was fine. Hey, no problem, right? We'll never run out of addresses. That's enough addresses for the population at the time for every man, woman, and child on the planet. Ridiculous, right? Except now we have these things called like mobile devices, phones, tablets. We usually have several of them. Pretty much, they're extremely common. The idea of running through 4 billion IP addresses nowadays isn't so far-fetched. So there had to be some things done to try to conserve these IP addresses. The actual solution was to implement IPv6, or to invent it. It has actually been implemented for years now. It's just not commonly used inside local area networks. And this is what we're talking about here, inside of LANs. So that entire 4 billion potential IP addresses are split out into 3 different classes of networks. I have Class A, Class B, and Class C. Hence the term classful networking. Now, in classful networking, I have some very firm definitions here that simply don't change. And I'm going to refer to the first octet. That's this number right here, right? The first octet, second octet, third octet, fourth octet. If my first octet is a value between 1 and 127, by definition, it is a Class A network. By definition, it has a subnet mask of 255.0.0.0. What that means is if only this first octet is a 255 and the rest is 000, only the first octet refers to the network, and the other 3 octets refer to the host. Well, 32-bit number minus 8 for that first octet gives me a 24-bit number. 24 bits gives me about 16 million possible IP addresses. So I don't have very many of these networks, right? Basically 127 of them. Actually 126, because 127 is a special case. But they got millions of IP addresses inside of them. Well, in reality, I can't use a subnet with millions of IP addresses inside of it. It can't actually implement. But the range is there. And then I have Class B networks. This is where my first octet, again, we're right here, is a value between 128 and 191. In classful networking, by definition, a network with 128 to 191 its first octet gets a Class B network mask, a 255.255.0.0 network mask. Now, these first 2 octets refer to the network, and the last 2 octets refer to the host. Well, 8 bits plus 8 bits, that gives me 16 bits. In 16 bits, I can represent 65,535 hosts. Okay, now in reality, that's still too many. But notice what I've got here. I've got really, networks with smaller numbers of hosts in them. I have more networks to pick from with smaller numbers of hosts in them. Let's take that the next step further. Class C networks. In a Class C network, this first octet must be between 192 and 223. So right here, this is a Class C network. And by definition, in classful networking, it has a subnet mask of 255.255.255.0. Actually, I have a typo on here. Look at that. Who wrote this slide? Oh, I did. The number of possible IP addresses in a Class C network is not 65,565. That's Class B. But what it is 254. Let me fix that real quick. There we go. There, that's better. Why is that the case? Because look, right here, I have 8 bits, 16 bits, 24 bits that refer to my network. So I have a lot of these networks, a lot of Class C networks. I only have 1 octet that refers to the host. So I only have 8 bits. The biggest number I can represent in 8 bits is 256. Why 254, you're saying then? Because there's 2 special addresses on any network range that I can't assign. One is the network number. Every network has a number. This network number is 192.168.1.0. That identifies a network. I can't give that to a host. My first assignable IP address in this range is going to be 192.168.1.1, right? My second one is what's called the broadcast address. Whereas this value right here refers to an individual host in the network. What if I wanted to talk to every host on the network all at the same time? It's like me going up in front of a large room and yelling, "Hey, everybody!" Well, that's a broadcast transmission. In this case, my broadcast address is going to be 255. So 192.168.1.255 is a broadcast, and I can no longer assign that either to an individual host. So my assignable IP addresses for this Class C network is .1 to .254. Well, here's the thing. Classful subnetting isn't difficult at all. You might be looking at this going, I don't see the connection. This doesn't make any sense. Well, we're looking at this in terms of decimal, base 10. Right? Human beings like thinking in terms of base 10 for really obvious reasons. The fact that I got 10 little fingers hanging off the end of my hand. Right? We evolved this way. Our hands were the earliest form of computer, if you will. A meat computer. It was an adding machine. 1 + 1 is 2. There it is right there. We think natively in base 10. But computers don't. Computers think in terms of binary, 0 and 1, and that's it. So networking doesn't make much sense in decimal, but it makes perfect sense when I express it in binary. Look what my net mask do. Right? There's my 255, and that shifts to here. I'm like, oh man, what is going on here? To truly understand what we're seeing right here, we have to understand how to go back and forth between binary and decimal. And there's actually a really easy way of doing this. Now, there's lots of different ways of doing this. You can do it mathematically in a powers of 2 type of thing. There's all kinds of little tricks for doing it. The method I'm going to show you right now was actually taught to me by a Cisco engineer years ago. And it just made sense. It works. And it works especially well for IPv4 networking. Because really, we're just doing simple math functions on 8 numbers, 8 bits. And if I can add 8 numbers together, or any combination thereof, we can totally do this. So let's take a look at it. Let's look at this in terms of a single octet. And this is an octet, isn't it? 8 bits. Now these aren't the bits per se, they're bit positions. But I have 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And what I do is I represent the bit positions, and I actually start at 1, right? So I start over here, and when we do this in binary, we move to the left. At every bit position I move to the left, I double. So I go from 1 to 2, 2 to 4, 4 to 8, 8 to 16, to 32, to 64, to 128. 1 bit, 2 bit, 3 bit, 4 bit, 5, 6, 7, 8. If I went to a 9-bit number, then my next number over would be 256. 10 bits would be 512, and so on. We don't need to do numbers that big, fortunately. IP networking keeps us down in 8-bit, in nice little 8-bit values. So that makes it nice. So I write out my bit positions just like this. And the way I calculate it, I light up the certain positions underneath it. And by that I mean I'm going to put in a value of a 0 or a 1. So how would I represent 8-bit, the 1 decimal in binary format? The number 1. Real easy. I go over here and I put a 1 under the 1 position. Remember, binary is only 0 or 1. That's the only possible values it could be. Everything else would get a 0. See what we did here? 0, 0, 0, 0, 1. This is actually how you represent an 8-bit number, or excuse me, the decimal 1 in 8 bits. I actually would have to spell out all 8-bit positions. So in 8 bits, the decimal 1 is 0, 0, 0, 0, 0, 0, 0, 1. See what I got going here? What about if I want to represent decimal 2? I would simply light up the 2's position and put 0 under the 1. Now, for the purpose of our discussion, I'm going to assume the rest of these are just zeros, okay, unless we do it otherwise. And then all I do is anywhere there's a 1 up in here, I add them together. So look straight up, there's 2. So decimal 2 is represented in binary as 1, 0. I have a t-shirt hanging in my office that says there are 1, 0 types of people in this world. Those that understand binary and those that don't. Well, now you get the joke. What if I want to represent 3? I simply light up the 2 and the 1 position. Add them up. Anywhere there's a 1. 2 plus 1 equals 3. Binary, 3 is 1, 1. If I want to represent 4, I light up the 4's position and 0 out the 2 and the 1. Now, I'm leaving the zeros over here as implied. Strictly speaking, they're not required, but they are required over here. Now, let me ask you this question. How many bits did I need to represent the value 0 or 1? 1 bit. Right here. How about to represent the values 2 or 3? I'd have 2 bits. 1 bit, 2 bit. So likewise, to represent the value 4, I need 3 bits. 1, 2, 3. So decimal 4, binary 1, 0, 0. What value do you think that is? What decimal value do you think that is? Think about it. Decimal 5. Add up the values, the bit positions that have the 1 above them. So 4 plus 1 is 5. Six. 7. And then we just keep pressing on. To represent decimal 8, I move over another bit position. and 0 everything out. And we just keep on doing this across all 8 bits. So using this, I can very easily represent the binary on the fly. How about this? What if I light up every bit position on here? What if I do something like this? I got all 8 bits equal 1. I add them together. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255. There's 256 possible combinations here. 0 is a valid combination. 0 and 255. Where have I seen that value before? Right here. Right? In classical networking, my subnet mask is either completely, the entire octet is completely lit up, or it's not lit up at all in classical. All right, actually, let's do one more. What about, like our IP address, what about our 192? How would I represent that? Well, I add them up. I start at the very beginning, and 128, that fits into 192. Okay, that's good. 128 plus 64, let's see, 128 plus 60 is 188, plus 4 is 192. And then everybody else gets a 0. (128 plus 64 is 192, and there we go. 192 in binary, 11000000. See where we're going with this? And using this technique, I can express entire IP addresses. And look at that, my slide actually slid off there a little bit. So you're going to get to watch me do a quick repair. Let's go back over. Oh yeah, look at that. Let me stretch this just a bit. There. There we go. That's better. I can represent all 4 octets using my 8-bit positions. There's the dots, remember? 1 octet, 2 octet, 3 octet, 4 octet. Each octet never goes above 8 bits, so I reset every single time. We just do what we just did, only in terms of each address. All right, so let's take a look at this. Let's say I want to represent, I don't know, let's do our 192.168 address. Let's do .1, .100. Now, to express the IP address, what I would do is I'd go through each octet and light it up. So we already covered this. 192 is lighting up my first 2 positions. 0, 0, 0, 0, 0, 0. Dot. 1, 2, 3, 4, 5, 6, 7, 8. 168. Well, let's light that up. 64 will go above 168, so that has to 0 out. 128 plus 32. Okay, that's 130. 160, so let's light that one up. 16 would put me over. 0. 8, there's my 168. Then everything else is a 0. Now those are pretty sad looking zeros, but you get what I mean. Next one's real easy. I just light up my 1's position. All right. Everybody else gets a 0. Hey, if you think this handwriting's bad, wait until you see my actual penmanship. And then, let's see, that's a 1. Right? And then 100. Well, I got a 0 at 128. 64 plus 32. That's going to be 96, so we get a light up to 32 position. 16 would go too high. 8 would go too high. What did I say that was? That was 64, 60, that was 96. So light up the 4 position. There we go. So it's kind of hard to read there, but there is our decimal 192.168.1.100 represented in 32-bit binary format. All right. You're like, that's still not way easier to understand. What are we talking about here? Remember what I said initially. An IP address by itself is a screen door in a battleship. It's useless to me. However, if I add the subnet mask, and that's 255.255.2. Oh, I know, this is horrible. 5.0. Let's represent that in binary. I'm going to do it directly under my IP address. Well, gee, classical networking is pretty easy, isn't it? 255. How do I get 8 bits to show me 255? I light everything up. Everything gets a 1. Dot 1, 1, 1, 1, 1. Notice I'm lighting them up directly underneath the other values. Dot 1, 1, 1, 1, 1, 1, 1, 1, dot 0, 0, 0, 0, and 0. There. That's 255, 255, 2550 represented in binary. Now, anywhere where there's a 1 means network identifier. Anywhere that's a 0 is host. It's obvious to me, right? Now, my subnet mask is always contiguous, which means I always have my 1s grouped together. I'll never have in a subnet mask something like this, where it's 1010001. No. It's going to be continuous 1s all the way over. So looking at this in binary, now it's very obvious to me where the division is. Anywhere there's a 1 represents, in my net mask, represents network identifier. Now there's also within each of the classes special IP addresses. Even back in the late 1980s, even before the internet became a thing, it was becoming obvious that this 4 billion IP address thing we're going to run out. We're going to be in some trouble here. So one of the ways that was devised to help conserve IP addresses was to define private IP ranges. These are IP addresses intended to be used inside local area networks for private use. These addresses are not routable on the internet. And if you try to send one of those addresses out to the internet, the first router it gets out there is going to drop it. So these are for internal use only. And every class has a private range defined for it. For Class A, the entire 10-dot network is deemed private. Right? This cannot appear on the internet, which means it's ours to play with if we want. For Class B, any address from 172.16 to 172.31, private. Now 172.12 is a public address, but 172.16 to 172.31, private. Likewise, Class C, anything in the 192.168 range is private. And that one looks real familiar to us because that's usually what home networking equipment uses for our IP addresses, right, by default. And as we've seen, it's a Class C address, so I have 254 hosts. It's a nice, good fit for home. Why are we even doing this? Is it just to make your life difficult? No, absolutely not. we need the internet is nothing but a collection of small networks, many millions of them, but just a collection of networks. Our IT infrastructures, likewise, are a collection of networks. I don't want all my hosts in a single network. I need to segregate them. I need to separate my traffic out. And I do this by using subnets. That's what that is. Sub-networks. Pieces, individual networks. In this case, we're representing it in a multi-story building. First floor, second, third floor. And every floor of the building gets their own network. Right? Here's one network. Here's another network. And here's another network. And these little devices right here, joining them together, routers. All together, they make up one network infrastructure. But what do routers do? Routers join networks together. And it joins these three together to allow them to communicate. Each of these networks gets their own address space. This network up here might be 10.1.1.0. This one down here, 10.1.2.0. This one down here, 10.1.3.0. I can have as many networks as I want as long as I have the equipment to allow them to communicate with each other. And that takes us to the end of our discussion on classful networking. When we come back and on our second half of our lecture, we're going to discuss classless networking. And these are the skills that are going to take you forward into our other classes like routing and switching, but most definitely into your career as an IT professional.